Hi there. Welcome to the first video for INFO640 or data analysis. We're going to start today with exploratory data analysis, which is just basically seeing what's going on with our data set. So first thing, I want you to open RStudio. RStudio is a integrated development environment for R. It makes a whole lot of things a whole lot easier. Once you open a new RStudio project, it should look like what you see on your screen here. RStudio is a circle with a big R in the middle. If you don't see that, please put your sticky up and I will come over and help you find it. So, you are looking at the RStudio terminal. Now, integrated development environments generally have a really useful set of features. Usually you can explore the data sets, you can explore the commands, you can see what's going on without actually having to run your code. Okay. This makes dealing with R a whole lot easier. And R is a programming language. It is similar to Python or C++ or things like that. R is what we call a very high-level programming language. What that means is that it's really designed for end users to use. You're not expected to be a developer or anything like that. You are expected to be a researcher who wants to find the answer to a question that you have, or something along those lines. So we've chosen R because it's open source, it's free, so unlike other statistical packages, you will always be able to use R. No matter what computer you're on, no matter where you are in the world, you will have access to R. If you are interested in open source or open source computing, please come and talk to me after class, and I would love to talk to you about it more. But for now, let's get started on some exploratory data analysis. Okay, so the first thing that we are going to do is load some of our libraries. Now, a library is kind of like a dictionary. So you can think about R as the structure of the language and the dictionaries as the vocabulary. So there are some built-in features to R, but just like if you were learning German or Japanese or any other variety of languages, if you know the structure, you can generally fill in the vocabulary. So libraries are kind of like that vocabulary. They tell R how to work. So the first library that we're going to load is called Fun Modeling. And go ahead, once you open up R, you should have this little arrow right down here. We are going to type next to that arrow. So we're going to load the library Fun Modeling. And you see here, what I love about RStudio is that it suggests what it thinks you're looking for. I don't know about you, but I make a lot of typos, and having RStudio autocomplete for me is really useful. So first thing, we're going to load the library Fun Modeling. So we're loading this dictionary of commands called Fun Modeling. Go ahead and hit enter. And it'll run some code. And it's saying loading the required packages. It means that all of these things are here. It's giving me these warnings down here. You actually don't need to worry about this at all. What these warnings are saying is that I have an older version of R running than Fun Modeling was, or a newer version of R running than Fun Modeling was built under. I can see my version of R up here, 3.4.2. And you see it's saying, wait, there might not be backwards compatibility. Don't worry about it. If you're just getting these warning messages and no error, it's not a problem. However, if you got an error, you might need to install the library. So if you have some sort of error here, go ahead and type install.packages and then Fun Modeling. And here, Fun Modeling has to be in quotes because if Fun Modeling is not yet loaded into your computer, then it doesn't know what it's called, so it has to have the quotes around it to figure out what this is going to look like. Don't worry too much about that syntax. It's actually not that important. Just go ahead and run this. Sure, I want to update that package. It's installing my package and it's updating it for me. It may do the same for you. Excellent. And once it finishes downloading those packages, you should get some message along these lines saying that the packages are in this folder that you should never ever access. Unless you really know what you're doing, do not try to access these folders. It's just where the dictionaries live, or the packages live. Okay, so we have our fun modeling library. We also want our tidyverse library. So I'm going to say library, and then I'm going to say tidyverse. And hit enter. It'll also give me some errors. Yeah, they're built under different models, not a big deal. Finally, we're going to load the library HMISC, HMISC. Go ahead and hit enter there. Nope, I must have hit shift enter, hit enter, and there it gives me the same kind of messages that one component of this is out of date. Don't worry about that too much. All right, so we want to know a little bit about the heart disease data set. So most data sets, you type a question mark and then the name of the data set. This one, because it's actually something that's packaged with the fun modeling library, we have to type 2 question marks. So we type 2 question marks, heart_disease, and hit enter. And then we get this information over here. So it's done a search of the R documentation, and we find the fun modeling package, the heart disease data set. So if we go ahead and click on that, we say it gives us a description. These are variables related to a patient clinic trial. The variable to predict has heart disease. So we'll talk later in the semester about type 1 and type 2 hypotheses, type 1 and type 2 errors. This has to do with how you frame your hypothesis. Here, this is telling us that the thing that can be predicted by the other variables is if the person has heart disease or not. We also find that it's a data frame with 303 rows and 16 variables. That means that there are 16 different dimensions on which they've measured whether or not, on which they collected data. And some of them predict whether someone will have heart disease, and some of them are non-predictive. And there are 303 data points. In this case, that represents 303 patients. This usage here just tells you how to type it in order to get it to come up. Okay, so the first thing that we want to do is just kind of get the broadest overview of it possible. So we're going to type glimpse and then heart disease. And it's going to go and fill it in for us. And then we hit enter. And I have a typo. This is an excellent lesson. Like I said, I have a lot of typos. So if you hit the up arrow on your computer, it'll go to the 1 row up and copy it. And then you can just go over and fix your typo. Okay, so we see that there are, again, 303 observations, 16 variables, and these variables are all of these things. Age, gender, whether or not someone has chest pain, their resting blood pressure, their cholesterol, all of these different things. So these variables are what do or do not predict if someone has heart disease. Okay, so we'd also like to know more than just what's in here. How many of these data points are missing? How messy is our data, really? So we'll do df_status, and then we'll pass heart disease again, and then we'll hit enter. And we see here that there's no none values for age, gender, chest pain, resting blood pressure. That means that all of these things have been filled in. Over here, we see the word unique. What that means is that there's 41 unique entries for age. If we look up here at our age variable, at our just, give me the table, let me see what it looks like. I see most of them are in the 60s, we have 67, 67, 37, 41. So what this tells us is that there's 41 unique ages. Here, for gender, we say that we have 2 unique genders that have been reported in our table up here. Chest pain, there are 4 unique variables for chest pain, which is interesting because you might assume that it means does have chest pain or does not have chest pain or something like that. So it's interesting that there's 4. We might want to go and look at that in a little more depth over here at the heart disease data set description. We have resting blood pressure, all of these things. If we look at this column here, we have integers, factors, and numeric. Integers, as you might expect, are generally whole numbers. So you see up here, no one reported that they were 63.5. People just rounded their age up to a whole number or an integer. Gender is a factor. Generally, that means it's a categorical variable, and it either fits into this category or that category. People reported that they were either male or that they were female. Chest pain, yes, every day, yes, sometimes, yes, occasionally, no, never, that type of thing. The other number that we have here is, or the other value we have here is numeric. Numeric just means that there's a decimal place. So it could be a fraction of a number as well. Finally, another important thing to look at here is what variables have a lot of zeros or no number here. And we see that fasting blood sugar has a lot of zeros. I think that this is an exercise test, has a lot of zeros. Given that there's only 303 records in this data set, 258 of them being 0 is probably more than we want. This is telling us that 85% are zeros. So we probably don't actually want to include those in our final analysis. Fasting blood sugar is probably not going to be a good variable for us to look at, simply because we do not have enough data across the population. So the first thing that we're going to do is select a few variables that we are interested in, because I'm not interested in all 16 of those. So I'm going to set a variable and call it my data. And I'm going to say my data is equal to heart disease. So I pull from that data set, and then I say %, arrow, %. Don't worry about that syntax for now. You'll see it throughout the semester as a way to select from data frames. And I'm going to say select age, comma, max heart rate, comma, THAL, comma, and has heart disease. Okay, the THAL is a type of test that measures the amount of blood that your heart is getting. I only know that because I looked it up on Wikipedia. Okay, so we are going to select these 4 variables from our overall data set so that it makes it a little bit more manageable to work with, and we can use some of the handy tricks that our studio offers us for exploratory data analysis. All right, go ahead and hit enter on that. And now our my data, just print that out and it will tell you everything that is in the my data dataset. It prints the entire data frame to the screen. I should take a break here and talk about data frames for a second. Data frames are just a large table with a couple of extra features so R can read them in a special way. If you've ever used Excel or any other spreadsheet in your entire life, you have worked with the structure similar to a data frame. It's just a really fancy type of table specific to R It's also used in Python and a lot of other programming languages. It's a way to keep your data organized. Okay. Yeah, we'll talk more about that as the semester goes on and as we move into Tibbles, but that is a little bit of foreshadowing. Okay, so now we are going to make our first chart of this data. We're going to do a frequency distribution, which is a simple function that runs for all factor or categorical variables. So it's going to run for all of our variables here. It treats numeric variables as categorical variables. So what I want you to type is FREQ and then pass it my data. But don't make a typo like I did. There you go. So freak my data. It'll take a second to run, but then you should see this table, and this table describes our data set here. And you should see a graph here of has heart disease, yes or no. So what percentage of the sample or the participants have heart disease, and which percentage of the participants do not have heart disease. Now, you might have very, very quickly seen another chart pop up. And if your R was running more slowly than mine was today, then you definitely saw it. That plot is actually in this viewer window, but you have to click this little arrow over here. It's kind of hiding, this little arrow. So if you click that arrow and go back, it'll show you another chart, right? And this chart gives us just some numbers, and we are supposed to decode those numbers. What the NA stands for is obviously not applicable. That's our data down here. And the 3 is up here. So for THAL has the values 3, 7, and 6. I personally don't know what those mean without going out to my data set and taking a look and looking up what 3, 7, and 6 means for this tall test. Obviously, you are welcome to go out and do that and take a look to see what this actually means to the layperson. Now, you might also notice that RStudio has not organized these in order because these are categorical variables. So RStudio thinks that 3 is a word, not a number. So rather than organizing this according to numerical order, R has organized this according to volume. So it said, oh, there's the most of this 3, second most of the 7, and third most of the 6. Because R cannot evaluate this value. All it can do is read this value. It reads it as something called a string. Again, don't worry too much about that. That is not really important for what we're going to talk about today. Now is a really good time to save your project, either with Command S or Control S, and that should allow you to save it to your computer. Now let's say that we wanted to export our graphs. So we could either go over here to the export button and save it as an image, or copy it to the dashboard. I'm going to cancel because instead of doing that, I want us to do it with code here. So we're going to say FREQ, freak, my data, and then path underscore out equals, and I want to save both of these to the current directory. So I'm just going to say path out equals 1 dot, and that gets me into the current directory. And it says that my variables were processed. So that means that they've been saved to the directory that I'm working in. And you can pause here and go ahead and go out and check to make sure that that actually worked. All right, so the next thing that we're going to do is analyze numeric values. So we're going to analyze them graphically. And the first way that I want you to do this is with plot num. P-L-O-T-N-U-M. Then pass it my data, hit enter, and you should get two graphs here. You have the age graph, and you have the count of people who have heart disease, and the maximum here. No, sorry. You have just how many people in the sample are of a given age, not relative to anything else. So how many people are in their 20s, how many people are in their 40s, their 50s, their 60s, their 70s. And we see a peak here in the 50s. This looks pretty close to a normal distribution, which is something that we're going to talk about later in the semester. We have another graph here. That's the maximum heart rate. And what this is what was the maximum heart rate for each participant in the study. Some it was down here in the 90s and the 80s. The majority were around 150 to 180, and then it starts to taper off. Also, this has a nice bell curve looking shape to it, which we will talk about later in the semester. One thing that you might notice here is that the variables that are plotted are different from the variables that are frequency plotted. So if we go back here to freak, we have has heart disease, yes and no. We have THAL, tall, which was a categorical variable or a factor variable rather than numeric. But here, when we look at plot num, it's only reading our numeric or our integer variables, so only things that can be analyzed numerically. This is helpful because if you just want to get a sense of what's going on with your data, how each data type is being processed, it's far better to go and look actually at the data type up here. Is it an integer or is it a factor? But just to give you a general idea of the distribution of these integers in your data set, it's really good to graph them out and just have kind of a better sense overall of what's going on with your data. All right. After visualizing it, we might want to go a little bit more in depth into understanding the mean and the variation within our data set. So we're going to use the profiling num. And I'm going to set a new variable, and my new variable I'm going to call my data prof. And I'm going to set my data prof equal to profiling underscore num, and it offers it to me. And then I'm going to pass the variable my data. Okay. What I'm doing here is creating another variable, my data prof, my data profile, and I'm going to set that variable equal to some kind of transformation on my data. We're going to talk about this later in the semester. For right now, I just want you to know that we've made a new variable that is all kinds of numbers about our data. Let's go ahead and hit enter there. All right, and we see here a whole lot of numbers. We're not going to worry too much about these. As the semester goes on, this will make more sense. The variation coefficient, the P05, P25, that kind of stuff. But for today, what I want you to focus on is the mean, which is our age mean is 54. Our max heart rate mean is 150, which is about what we were seeing here. We could have assumed that these were evening out to be around, mid-50s. And 150 looks to be about the max, apparently even on both sides as well. We have our standard deviation here, which is how much on one side or the other is the average deviation from this mean. So 54 plus or minus about 9 years. So we have 45-year-olds is the average standard deviation, and 65-year-olds is the average standard deviation. Again, we're going to talk far more about standard deviation as the semester goes on. The last thing I want to point out here is the range. So we have The range of 98% of the data is age 35 to 71. The range for 80% of the data is 42 to 66. Now the 98% includes all but the furthest outliers. It's generally considered a little bit safer and a little bit more conservative to use the 80% range, which means that 80% of the participants are between ages 42 and 66. Now, particularly for age, you're probably just going to report the entire range, but let's say that you had a 110-year-old in your study. People live to be 110, so it's completely reasonable that there could be a 110-year-old in your study. What that would do would dramatically change your mean. However, you probably only have one. So either the 98% range or the 80% range would capture the majority of people within your study. Again, this is just a preview, and we're going to talk more about this as the semester goes on. But for right now, this is just meant to give you a sense of how we can look at our data to get an understanding of what's going on with our data, our exploratory data analysis. Finally, let's say that I wanted to explore or analyze my categorical and my numeric data at the exact same time. The HMISC package has a really useful feature for this. So we can say, quite simply, describe, and then pass it the variable my data. And I say, okay, go ahead and describe my data. And it gives me all of this information. I'm going to move this over a little bit so we can see a little bit better. It says I have 4 variables, 303 observations. It tells me how many are missing in the age category, what the mean is for age. It tells me how many are missing in the heart rate category, what the mean is for heart rate. It tells me how many are missing in the tall category, how many are distinct, the frequency and the value, and how many are missing in the has heart disease category, the frequency and the value as well. And this is generally the best way to get a snapshot of both your categorical variables, your tall and your has heart disease, as well as your numeric variables, your age and your max heart rate. This ends our exploratory data analysis for the day. If you have any questions, put up your hand or your sticky and I will come over to talk to you about it. And have a nice evening, and I look forward to seeing you next week. All right, bye-bye.